Welcome to Shanti-Peace for Mathematics. In this lecture, we are going to develop a mathematical tool for study a rate of change of that involves functions of two or more independent variables. So let us recall first variable case where you are studying rate of change. You are given a function y equal to f of x, and if you want to say that this function derivative is exists, then you know that you are using this definition limit delta x tends to 0 f of x plus delta x minus f of x upon delta x is exist. Then you can say that the function is differentiable at point x, and this quantity is nothing but the df by dx, and that is instantaneous rate of change of f with respect to x. Now here the situation we have a z is a function of two variable x and y. Obviously one can ask a question that if I want to know what is the rate of change of z with respect to x keeping y as a fix, and another question one can ask is what will be the rate of change of z with respect to y keeping x fixed. For example, if I have a rectangle whose height is a and breadth is b, if I consider, then the area of this rectangle is a function of two variables, that is a into b. Now if I fix its breadth, this I will fix, and if I allow or I am varying its height, so maybe I am varying its height, then how much rate of change of that with respect to a you will have keeping b fixed. That means breadth fixed and you are changing its height. Then what is the rate of change of area you will have? Same question, if I fix its height and allow its breadth to increase and decrease, then how much rate of change of the area in that you have. Same example if I consider in the physics. Suppose I have one gas chamber. In this gas chamber there is a gas is filled up, and a pressure, whatever the pressure create in this gas chamber, it will depends on two things, a gas volume plus gas temperature. How much temperature is there in this chamber. Now I want to find out what will be the rate of change of pressure with respect to gas volume if I fix the temperature, and also vice versa, what is the instantaneous rate of change of pressure with respect to temperature if I fix the gas volume. So now with this idea we are trying to describe what is the rate of change of functions of two variables. Suppose that you have given x0 y0 point which is in the domain of the function f of xy. Now we fix this y equal to y0. Now if you can see this, observe this f as a function of x comma y0. So this is actually a function of one variable because now we have fixed your point y equal to y0. Now we can talk about instantaneous rate of change of this with respect to x, that is d by dx at f of x comma y0. The value of this derivative at x0 gives the measurement of instantaneous rate of change of f at point x0 y0. Similarly, if I fix x is equal to x0, then z is equal to f of x0 y is a functions of only one variable y, and then I will talk about what will be the dz by dy, that is d by dy of f of x0 y. Instantaneous rate of change of f with respect to y keeping x. By definition, you know it is the x0 y at point y equal to y0. We know by definition it is a rate of change. But if I use the definition of the derivative for one variable, we know that it is delta y tends to 0, because here x0 is fixed. So it is x0 y plus delta y minus x0 y upon delta y is there. What I just did is I just make it change in y only. As you see in the above definition, that is in the derivative definition, you can see that it is, you are changing in x. So in the numerator you have actually change in f. In the denominator you have change in x, where x is an independent variable and f or y is a dependent variable. Here is the same thing. You have the z is a dependent variable, only we are allowing vary y, so that's why change in y is only there, and x is a fix. So this is actually a partial derivative. So this is actually a definition of a partial derivative of f with respect to y. So it is denoted as fy at point x0 y0. Similarly, d by dx of f of x y0 at point x is equal to x0 will be limit delta x tends to 0. Now here x is a variable, so I am just changing in x here, and your y is fixed, minus xy0 upon delta y, and this will be denoted as fx at point x0 y0. So these are the relationship of partial derivative and its derivative of the functions of one variable. Let us have the example. Find fx at 1 2 and fy at 1 2. If I have given f of xy is x cube y square plus x square plus y square plus 2. Now as per this definition, fx at x comma 2, then what will be this? It is actually a d by dx of f of x, because we are keeping y fixed at 2, because that is the point we have given here. Now you know that d by dx of, if you fix your y equal to 2, so you substitute the value of y here, you will have x cube into 2 square plus x square plus 2 square plus 2. So if you simplify, this will be 4x cube plus x square plus, this is 4 plus 2, it is 6. Now derivative of this quantity will be 12x square plus 2x, and at point 1 2 partial derivative of f, you will have 12 into 1 square plus 2 into 1, that will be 14. Same way, if you can calculate fy, now the point is 1, so I am fixing x is equal to 1 here, so 1 comma 2, that is d by dx dy of f of 1 comma y here, that is d by dy of 3. Now you can just substitute x is equal to 1 here in this equation, so it is 1 cube y square plus 1 square plus y square plus 2. So if you can simplify, this will gives you dy by dy will be y square 2y square, because this is y square plus this y square, 2y square plus 3. Now the derivative of this will gives you 4y, and at point 1 2 the answer is 8. So that is the keeping one variable fixed, taking the derivative. Now we'll see the partial derivative as a function. So here what is the situation in the above example and above definition? What is happening? You are fixing your x is equal to x0 and then you are calculating what is fy at point x0y, and finally you will have the answer at point x0 y0. But it may happen that I want to calculate the partial derivative of f with respect to y at any point. This is at the point x0 y0 we have calculated. So for that we'll have this definition as a function in this manner. For any point fx at xy can be defined as f of x plus delta x comma y minus f of xy upon delta x as delta x tends to 0. So what is we are changing here? We are changing x, y keeping as a constant, but now it is a function of xy. For any point you can calculate this, and fy at point xy will be limit of f of x comma y plus delta y minus f of xy upon delta y as delta y tends to 0. So this is the notation for denoting the partial derivative. It's also denoted by del f upon del x, and this will be denoted by del f upon del y. So these are the notation for partial derivative of the function. For example, let us have the same example. We'll calculate f of xy. In the previous example was given as x cube y square plus x square plus y square plus 2. But the question is to calculate fx at 1, 2 and fy at 1, 2. Now what we will do is we keep y fixed, derivative of this with respect to x, that will be denoted as fx at point xy. First of all, you know that the derivative of d by dx of f plus g will be derivative of f plus derivative of g will have. So using this quantity, what we can say is the derivative of whole quantity will gives you derivative of this plus derivative of this plus derivative of this plus derivative of this. But if I try to take the derivative of this first quantity, I am keeping y fixed. So this y square you have to fix, that is as a constant you have to treat. So y square as it is, a derivative of x cube is 3x square. Here the derivative of x square is 2x. This y square is a fixed value when you are differentiating with respect to x. So that is a constant, and derivative of a constant is 0, and derivative of 2 is also 0. So fx is this. Now fx at point 1, 2, you will have 3 into 2 square into 1 square plus 2 into 1. So that is 4 into 3, it is 12 plus 2, it is 14. And fy at xy in the similar manner. Now you have to differentiate this equation with respect to y and keeping x constant. So what you will have is your x is constant, so it is x cube is constant. The derivative of y square is 2y plus the derivative of x square will be 0 because it is a constant, and derivative of y square will be 2y, and derivative of 2 is 0. So fy at 1, 2 will gives me 2 into 1 cube into 2 plus 2 into 1. So 2 into 2 because y is 2. So that's why it is 4 into 4, it is 8. So that is the matching with the previous things which we have did. So as I told you, notation for this partial derivatives are del f upon del x, del z upon del x also can be represented if z is a function of f of xy if you consider. So these are the notation for partial derivative of f with respect to x. Same way, partial derivative of f with respect to y, it's denoted by this notation or it is by this notation. Don't use d. Okay, so this is delta. So please differentiate these two notation. This is d and this is delta. So they are the different notations we are using here. Okay, let's have the another example. Find del z upon del x and del z upon del y if z is equal to cos of x into y. So if you differentiate this del z upon del x, so you should keep in mind that this is a functions of two variable, but when you are differentiating with respect to x partially, then your y is constant. So first derivative of cos is, it is a sine of xy minus sine of xy. Then the derivative of xy is there, partial derivative of xy is there. That will gives me sine of xy, and the partial derivative of x with respect to x, you have to keep your y constant, so that will gives me y. So finally the answer is minus y sine of xy. Same way, del by del y of z will be del by del y of this cos of xy. In the similar manner, the derivative of cos is minus sine of xy, and derivative of partial derivative of xy you will have. You fix your x and y vary. So derivative of x is, it is a constant. So derivative of x into y, where x is constant, will be x. So minus x sine of xy will be the answer. Now we'll talk about the geometrical interpretation of the partial derivative. How the geometrically the partial derivatives represent. So you know that when you have a functions of one variable, f of y is equal to f of xy is given to you, then the value of its derivative, that is f dash of x0, if x0 is on this in the domain of the function, it is interpreted as the rate of change of y with respect to x at point x0, or it will be gives you slope of the tangent to the graph of f at x0. So that means you have, this is your xy plane, this is the curve y equal to f of xy. So suppose this is the point x0, a tangent at this point x0 comma f of x0, a slope of this tangent is nothing but the f dash of x0, that you know. Okay, that is the geometrical interpretation of the derivative for one variable you will have. Now the same analogous will be useful to describe the geometrical interpretation of partial derivatives. Suppose you have given one surface, that is z is equal to f of xy. It is actually a function. Now I am fixing y equal to y0 fix, and whatever the intersection of these two surfaces, why I am saying it is the surfaces, because this will represent one surface, this is also represent a plane, so they are the two surfaces and they intersect. Whatever the intersection of these two surfaces is there, I am calling it is C1, and this is one surface, another surface is x is equal to x0, this is also a plane, so the intersection of this surface and this one, whatever the intersection of these two surfaces is there, the intersection will become a curve, and I am calling that curve as a C2. Now what does it mean of fx at x0 y0? it is actually the rate of change of z with respect to x along the curve C1 at point x0, y0. What is this? Is the rate of change of z with respect to x along the curve C1, and Fy at point x0, y0 will be a rate of change of z with respect to y along the curve C2. So let us understand this thing in the graphical. So here, this is the surface z is equal to x square minus y square is plotted. This is the surface is look like. What we will do is we see the what is the partial derivative of this surface with respect to x at the point 0, 0. That means we are just taking the cross section y equal to 0. So first of all, we'll put it the cross section y equal to 0 plane here. So if I put the y equal to 0 plane, it will be look like this. Now you can see that the intersection of this surface and this plane will be a curve, and that can be represented with this black curve, and the same cross section of this curve and this red line, which is a tangent to that curve, which is your slope of that line at that point 0, 0, which is the cross section is represented here. Now what I will do is I just change this cross section as well as, so if I change this cross section, according to that this point will also move. So you can see the representation of that one here. So if I'm changing this point, you can check the values. If I changing these points, according to that this plane is also changing and that tangent line is also changing. So the slope of this surface will be represented by del z by del x in x direction. So now let us see the same thing with respect to the y direction. Okay, so I'm starting with again. So in the y direction, this is the thing, this is the surface you will have. Now with respect to the cross section, I'm drawing the plane x is equal to 0.5 first. So if you can see that this is the plane with the intersection with the surface, and x is equal to 0.05 plane is this, and at the point minus 2.9 0.5 the derivative, that means the slope is minus 1. Slope of this line will be minus 1. That can be represented. Intersection of this surface and this plane will be represented by this a black curve, which is also represented here. Now here also I'm just changing these values, and according to that this tangent line, a slope of the line or tangent line will be changed. So this is the actual representation of or geometrical interpretation of a partial derivative of z with respect to x and with respect to y. So what is the partial derivative of z with respect to x gives you? It will gives you a slope of the surface in x direction, and the partial derivative of y will gives you a slope of the surface in y direction. So let's go back. So let's have some example related to that. Let f of xy is a function given you as x square y plus 5y cube. The first question is, I can say that find the slope of the surface z is equal to f of xy in the x direction at point 1, 2. Second one, find the slope of the surface z is equal to f of xy in the y direction at point 1, 2. Here what you need to find out is slope of this surface at the point 1, -2 in the x direction. So obviously in the x direction, that means we need to calculate what is del f by del x. The function f of xy is given as x square y plus 5y cube. So differentiation of this, partial differentiation of this with respect to x, keeping y as a constant. So your y is a constant quantity, so you will have 2xy, and this derivative of this one is 0. At point 1, -2, you will have is 1 into -2, that is -4. So the slope is -4, so I can say z is decreasing at the rate of 4 unit per as x is increase. Same way, if I calculate del f by del y, if I differentiate this quantity with respect to y now, so that is x square, which is constant, derivative of y is 1, plus 15y square, derivative of 5y cube, derivative of y cube is 3y square, so it is 15y square. Now at point 1, -2 will gives you 1 square plus 15 into -2 square, so that is 60 plus 1, that is 61. So that means f or z is increased at the rate of 61 per unit increase in y. So that's the way to see the slope of the surface in x direction and in the y direction as I shown in that figure. Let's have the another example, same kind of. Find the slope of the sphere x square plus y square plus z square equal to 1 in y direction at point 2 by 3, 1 by 3, 2 by 3 and 2 by 3, 1 by 3 minus 2 by 3. First of all, what is given, it is in sphere, so it is implicit function is there, so that has to be two functions are related to this one equation is given. So let us try to see what is this sphere is you have given. So that is, let us say you have, this is the sphere, an intersection of this sphere with y equal to at this point, that is 2 comma somewhere this 2 by 3 1 by 3 2 by 3 point is on the upper hemisphere, and the point this, that is 2 by 3 1 by 3 minus 2 by 3 is, it is in lower hemisphere. This point is in somewhere here, so that's why this function will divide into two parts. The first one is 1 minus x square minus y square, and another one is minus of 1 minus x square minus y square. We need to find out the slope of this surface in y direction. So I have to differentiate this is with respect to y, and that I need to calculate at this point. So let us calculate that del z by del y will be, this is the square root of the thing, so you know that the derivative of square root is 1 upon 2 square root, so that is 1 upon 1 minus x square minus y square into derivative of this 1 minus x square minus derivative of 1 is 0, derivative of x square with respect to y is 0, and that is derivative of y square will be 2y. So you will have minus 2y upon 2 into 1 minus x square minus y square, 2 will be cancelled out. So you will have del z by del y at point 2 by 3, 1 by 3 and 2 by 3. So at point this, so it is, if you substitute, that will be minus 1 by 3 upon square root of 1 minus x square, that is 4 by 9 y square, that is 1 by 9. So if you simplify, this is minus 1 by 3. If you take LCM, that is 9 minus 4 minus 1 by 9. So that's why you will have is minus 1 by 3 upon, this will be 4 by 9. The square root of 4 by 9 is 2 by 3. So finally you will have minus 1 by 2. The slope of the surface at point 2 by 3, 1 by 3, 2 by 3 in the y direction will be minus 1 by 2. Similarly, I am giving you as an exercise the other things you got to calculate. If you have z, which is minus of 1 minus x square minus y square, find the slope of this z in y direction at point 2 by 3, 1 by 3 minus 2 by 3. So you can calculate this. So I will stop here. If you like this video, please press the like button. If you have any comments, suggestions and a question, please drop down in a comment box below. See you in next video. Bye bye.